So here is section 11.4, which is the important things here we have to learn is the cross product. We already know how it's going to be the dot product by multiplying each component. The cross product is going to be different. And we're going to work, but like we're going to use the cross product in 3 dimensions. So how is going to be the cross product? They give you an example here, and here is, in fact, this is the definition of the cross product, but you can use this one only if you have 2 terms, two vectors. If you multiply u times v. So you're going to use this rule, but how we can find this rule? So we're going to use a general form. It's going to be easier for us to remember how we're going to do the cross product between 2 vectors. How is going to be the general form? You see with this one, you're going to start from u2 v3 minus u3 v2. So it's a little bit confusing if you want to remember this one. So instead of that, let's figure out from here. I'm going to show you different page how we're going to do the cross product between u and v. So if you have 2 vectors, let's say u, we're going to write down the vector with the component I and j and k. Exactly that's what they asked. See? So u1 I plus u2j plus u3k. And let's v equal v1i plus v2j plus v3k. So this is u and v. Now we need to find the cross product between u and v. Be careful, it's not dot product. With the dot product, you're just going to multiply u1 times v1 plus u2 times v2 plus u3 times v3. With the cross product, no, we're going to convert this one to a matrices. Let's say here's the I, and here's j component, and here's k. And always, this is a plus, minus, plus. Because we're going to work with the 3 dimension. So always, if it's 4 dimension, it's going to be plus, minus, plus, and the other unit vector, the standard unit vector is going to be minus. But we're going to work only with the 3 dimension. So always we're going to start with plus, minus, plus. So always the j is going to be minus. Let's write down u1, v1, sorry, u2, and u3, and the second vector v1, v2, and v3. Now we need to find the cross product, which is going to be exactly the same definition for the cross product between u and v. So I'm going to start with the I component. So when I start with the I component, what I'm going to do, I'm going to hide the I component. I'm going to say, okay, because it's the I, so I'm going to hide it. So I'm going to say this is going to be equal. Then exactly like when you need to find the determinant for the matrix, u2, I always start from this one, u2 times v3 minus u3 times v2, u3 times v2. This is for the component I. Now I need to find the component j. So here's the minus. For the component j, I'm going to hide this one. So it's going to be u1 times v3 minus u3 times v1. This is for the component j. For the component k, it's going to be plus u1 times v2 minus U2 times V1, the component K. So this one is easier to find the dot product. This is only multiply two vectors. And we're going to see how it's going to be when we multiply three vectors. We can do the same thing, but it's going to be a little bit different. So for now, we're just going to use the cross product between two vectors. Then we're going to use the same techniques to find the area and the volume, but we have to add the triple product so we can find the volume. A cross product between U and V. So here is U, which is 1, -2, and 1. And V is a 3, 1, -2. So now we're going to hide the I. So it's going to be -2 times -2 minus 1 times 1. So -2 times -2 is going to be 4. 1 times 1 is going to be 1. Now we're going to hide the J. 1 times -2 is going to be -2. And 1 times 3 is going to be 3. So -2 minus 3. This is for the J. Then we're going to hide the K. So 1 times 1 is going to be 1 minus -2 times 3 is going to be -6. And there is minus, so plus. This is the cross product between U and V. We're going to do the same thing here. For this one, always when you multiply, when you do the cross product between V and itself, the same vector, always the result is going to be 0. Let's check that. For C, so always check, you're going to multiply this vector by itself. Let's check, it's going to be 0. So for the I, I'm going to do the steps here. For the I is going to be 1 times -2, that's -2 minus -2 times 1 is going to be -2. And there is minus, so plus 2. This is for the I. So you see the component I is 0. Let's go to the J. It's minus. I'm going to hide the J. Let's check the J. 3 times -2 is going to be -6. Minus -2 times 3 is going to be -6. And there is minus, so it's going to be +6. This is for the J. Let's check the K. Plus, for the K, 3 times 1 is going to be 3. Minus 1 times 3 is going to be 3K. So this one is 0I minus 0J plus 0K. That means the result is going to be 0. So always when you multiply a vector by itself, the result is going to be 0. And we will see that when we do the examples. Any questions so far about the cross product? You will see when we find the lines and the planes, the distance, we're going to use the cross product, and it's going to be easier than use the dot product. So there's a proof for this theorem. The important fact, if you remember, for the dot product, I'm talking about the dot product, dot product with the V is going to be V dot product with the U. But with the cross product, is going to be the opposite thing. That means U cross product with the V is going, when you flip these two vectors, when you say V times U, you will see the component I, J, K is going to be with negative sign, with different sign. For example, if you have U is like -2I plus 3J plus 2K. And V is going to be, let's do just numbers, 3I minus 2J plus K. So when I multiply U cross product with the V, the result, and when you multiply V cross U, the result for this one, if it's positive I minus J, for example, plus K, if the result for the cross product U times V, the cross product for V times U is going to be negative I, positive J, minus K. So it's going to be the opposite. That means this is exactly the same thing, negative. And here's I minus J plus K. That's why they said U cross product with V equal negative V cross product with U. This is just a simple example for the first one. Now, associative property, cross product, you're just going to distribute. Same thing here, you're going to distribute the scalar. If you multiply the scalar with the first one, it's the same thing. When you multiply the scalar with the second one, the cross product between U and 0 equals 0. This is the same thing. This is important because the cross product, any vector by itself equals 0. The cross product by any vector by itself equals 0. U and V, non-zero two vectors, and the theta is the angle between U and V. U cross V, the cross product between U and V is always orthogonal to U and V. For example, I'm just going to do it here. So if you have two vectors, U and the vector V, let's say this is U and this is V. The cross product between U and V is another vector. U cross product with V is always orthogonal with these two vectors. Is always orthogonal with these two vectors. That means the angle here is 90 and the angle here also 90. So the cross product is going to be another vector is always orthogonal to U and V. So we're going to use this one because this is really important note. And if you remember, the dot product, the length of the dot product I'm talking about is going to be the length of U, the length of V, cosine theta. With the cross product, it's going to be sine theta. U cross product with V equals 0 if and only if U and V are scalar multiples. U cross the length of U cross product with the V, you see the length of the cross product, always this is really important. There's a proof for this one, but we're going to use it to find the area for parallelogram. So when they ask you find the area, you're just going to, they're going to give you two vectors, like the length and the width. That's it. So when they ask you find the area, it's a parallelogram. It's hard to use the easiest way, but the easiest one is to find the cross product between U and V is going to be the area for the parallelogram. So the length of the cross product always is going to be the area of the parallelogram. So this one is really important, and we're going to use it to solve an example. So let's keep going. And here's an example. I'm just going to show you with this example. If you have U and V, the cross product. So here's U and here's V. The cross product, here is the result. You see this vector? this is the cross product, is always going to be orthogonal on U and V. Always orthogonal on U and V. Now, here's the question. How I'm going to check it's orthogonal on U and V? Like I'm going to find the cross product. Perfect. So I have U and V, and I found the cross product. They're saying that the cross product always orthogonal on U and V. So if you do the dot product between U, which is the cross product, and the dot product with the U, the result always 0. If you do the same thing, the dot product between U cross V with the V vector, the result is going to be 0. So that's why the cross product always orthogonal on vector U and vector V. So you can check that by using the dot product. Let's keep going. This is the example with numbers. We're going to do the same thing when we work on the examples. So here is the length of the cross product, which is going to be 1/34. The length of the cross product, that's mean it's the area going to be for the parallelogram. If you have a parallelogram, this one is going to be the area, because it says the length for the cross product always going to be the area. A unit vector, which is the same thing. Remember when they ask you normalize or find a unit vector. Find a unit vector, that means the length of this vector is going to be 1. So how are we going to find the unit vector for the cross product? Here's the cross product, and here's the length. We're going to multiply each component for the cross product by the length. We're going to divide each component from the cross product by the length. So the new vector, or the length for the new vector, which is U cross V, divided by the length of U cross V, is going to be equal 1. So if you're going to find the length for this vector, it's going to be 1. Because they ask you to find a unit vector. And always this unit vector, because we're going to normalize the unit vector. For example, if you have here's this is U, this is V, and this is U cross V. So U cross V, or the cross product between U and V, is always orthogonal on U and V. So if we need to normalize this vector, so when we normalize this vector, we're going to find a new vector. The length of the new vector equal 1. Not the length. Let's say this one, the vector is W. The length of the new vector equal 1, and still orthogonal on U and V. The length for the new vector equal 1, because it's a unit vector, and the unit vector is going to be still like orthogonal on the vector U and V. They can tell you find a unit vector or normalize the cross product. This is they're telling you when we can use in physics, find the torque, the moment of the force, how we can use it in physics, And I think there's an example. So here's another important thing to find the volume. There's another product, it's called the triple scalar product. I was going to be, let's go back here. So you see, now we have three vectors. Now we have three vectors. How are we going to multiply these three vectors? It's U times the cross product between V and W. So you say, oh, we're going to do the same thing. Yes, you can do the same thing, and instead of using there's no definition, you see, so we have to do the same thing. But now in this case, how are we going to do that? We're going to check that in an example. To find the triple scalar product, what we're going to do? We're going to do a simple technique here. For this one, because this is important to find the volume. So the first thing what I'm going to do, the same techniques, plus, minus with the J, and here's a plus. So U dot product with the V, cross product with W is going to be equal. Now we have three vectors, 1, 2, 3. So I'm gonna say for U1, because we're gonna take this number, cross this line, and cross this line. So for the U1 is going to be V2 W3 minus V3 W2. This is for the I. So that's the difference. That's mean you're gonna get a number from here, then you're gonna multiply U1 by this number. Now let's go with the J. With the J is going to be U2. Then I'm gonna cancel, and don't forget it's a negative. Don't have to put equal sign. It's a minus. This is for the J. So it's going to be the second one, which is U2. I'm going to cancel this one and this one. So it's going to be V1 times W3 minus V3 times W1. This is for the J. Plus for the K is going to be U3. U3, I'm going to cancel this column and this row. So it's going to be V1 W2 minus V2 W1. This is for the K. So write down this because you're going to find it here in the slides. That. So the next one is, you see here is area of the base and the volume of the parallelogram. It's going to be the length of the triple scalar product. To find the area, always it's the length of the cross product. To find the volume, as well it's on here, is going to be the length of the cross scalar of the triple scalar product. Okay, this is just to find the area. That's it. There's an example here after that, but we're gonna jump to do the examples on the side.